Okay, in the last lesson, we talked about limits, and now we are going to explain all the different kinds of limits there can be and do it in a qualitative way just by using a graph. And then after this lesson, we will actually evaluate limits of various functions. So here we have a function. Notice it starts down here and goes up here. Should be a little dot right there. Okay. And then comes over and goes up and goes back down and comes down and then starts squiggling all over. So we're going to use this to answer these questions, and let's just take them one at a time. First of all, what is the limit of the function as x approaches -6? So here we are at -6. As x gets closer and closer and closer to -6, notice that the value of the function gets closer and closer and closer to 1. It comes in from both sides, and the value of the function then gets closer and closer to 1. So there is our answer. It's easy as that. Notice in this case that if we evaluated the function at -6, we would also get 1. So the value of the function is equal to the limit at that particular point. At -4, as we approach -4, first of all, notice that there is no value of the function there. The function isn't defined at -4, but we can ask what's the limit, and as we approach -4 from both sides, the value of the function is getting closer and closer to 3. So we have a limit, but we don't have a value of the function. At -2, we do have a value of the function. At -2, the value of the function is 9. So there's the value of the function, but the limit is something different. If we were to ask what's the function getting closer and closer to as x gets closer and closer to -2, here the answer would be it's getting closer and closer to, should be a 5. So the limit is 5, the value of the function is 9. How about at 1? How about at 1? Well, let's see. At 1, first of all, notice that there's no limit. As you approach 1, the function is approaching 7 from this side, and it's approaching 5 from this side, so there's no unique value that the function is getting closer and closer to as you approach 1 from both directions. So the answer to this would be no limit or doesn't exist. The limit doesn't exist. However, as I just said, it is the case that as you approach 1 from the right, then the value of the function approaches 5. So the whole idea of these limits is just to give as much information as possible about the function. So here's what we do. We say, hey, this is called a one-sided limit. The limit as you approach 1 from the right, so we put a little plus there to indicate you're coming in from the right, and the limit there would be 5. And now you can probably anticipate what would happen if we would approach 1 from the left. As we approach 1 from the left, the value of the function is getting closer and closer to 7. So to indicate that, we put a little negative sign right there, and then this would be 7. That's all there is to it. Okay, so those are called one-sided limits. A limit doesn't exist, but it does exist from the left and the right. What about at 3? There's no real number that this function is approaching as x approaches 3, but it is getting arbitrarily large. It's going off to positive infinity in both directions. So we could write doesn't exist here, which is the case, but that's not as informative as explaining why it doesn't exist. It doesn't exist because it's going off to infinity. So we can put infinity there to indicate that it's on both sides, it's heading up, getting arbitrarily large. What about as we approach 5? As we approach 5, coming from the right, it's going off to infinity. As you approach 5 from the left, notice it's going to -infinity. So again, if you were to answer this question, we would say that it doesn't exist. There's no limit as you approach 5 coming in from both directions. But same as with this one, we can do a little more than that. We can say, okay, as you approach 5 from the right, the value of the function is going off to positive infinity. And as you approach 5 from the left, make this a little negative sign instead, then it's going to negative infinity. Let's do that a little bit better. Like so. So there you go. So that's just about it. There's only one other kind of behavior that a function can have, and we will see in the next lesson or so a function that actually looks like this, where as you approach a number, even just from one side here, it just starts squiggling, say up and down like this, just arbitrarily fast. It just goes crazier and crazier, up and down, up and down, up and down as you approach 9. So this would be a case where even from the left-hand side here, if you were to say what's the limit of f of x as x approaches 9 from the left, there'd be no limit. It doesn't exist. Even coming in from one direction, it's not going to infinity, it's not approaching some number. Here's where you have no choice but to say it does not exist. So there's that. Okay, another word, which is an important word having to do with functions, is the word continuous functions. To be continuous. Something is continuous if there's no breaks in it. If you think of trying to draw something on the Etch-a-Sketch. Did you ever use an Etch-a-Sketch? You have no choice but to just squiggle up and down. You can't break it and do anything like that. When I used to write my name, I had no choice, but I couldn't dot my I the way you're supposed to be able to dot an I on an Etch-a-Sketch. So a function is continuous if at any given point you can draw it without taking your pencil off the paper, as it were. So it's continuous right here, it's continuous here, it's continuous here, at all these places here, it's continuous. Because right here it's continuous, because I can draw it without taking my pen off the paper, off the board in this case. The definition of continuous, f is continuous at x equal a if three things have to happen. The value of the function has to exist. The limit has to exist. And finally, the limit has to be equal to the value of the function at a. So at all of these points right here, notice that that's true. Right here, the limit of the function at this point, say it's whatever, 4, the limit of the function is this value, and that's also the value of the function. Right here, look at what happens at -6. The limit is 1, and also the value of the function is 1. So it's continuous there. What about at -4? Well, -4, notice there's a break. And sure enough, that violates this one. Oops, I'm sorry. That violates this one. There's no value of the function at -4. F of -4 doesn't even exist. Okay, what about right here? Right here, it's not continuous. Why? Because even though the function exists, there's the value of the function, and even though the limit exists, there's the limit is not equal to the value of the function. The limit is 5, and the value of the function is 9. So they're not equal, so it's not continuous. We say it's discontinuous at -2. At 1, it's also discontinuous because there the limit doesn't even exist. The one-sided limits do, but not the full limit. At 3, it doesn't exist because the value of the function doesn't even exist at 3. It just goes up along the asymptote. Same thing at 5. The value of the function doesn't. And here, finally, when it just goes crazy up and down, there's no limit, and so the function is not continuous there. So to be continuous means that basically you can draw it nice and smooth without any break. So it's continuous there, but at all these other places, it's discontinuous. So those are the key words. They all kind of make sense. The word continuity is a good word to have chosen mathematically for that because it kind of has the same idea that it does in everyday use. So I'll mention just one other thing. And a nice way of saying that something is continuous is to say that the limit of f of x as x approaches a is equal to f of the limit of x as x approaches a. I like this definition myself because basically the limit of x as x approaches a is just a. So this is just a fancy way of saying a, but really what it does is it says that something is continuous if you can bring the limit inside the function. If you can bring the limit inside the function like that, then it's continuous, and we'll be using that from time to time throughout the course. So there's qualitatively what it means to have limits, one-sided limits, infinity, that sort of thing. And so in the next lesson, we'll actually evaluate a lot of functions and find out what the limits are.